Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we continue talking about GPU programming and optimization, and in particular we are going to talk about key GPU performance considerations. What are the things, the most important things that we have to take into account when we are trying to write code for GPUs that is high performance? But before we go into the details, let's very quickly recap on what we covered in the previous lecture. We were talking about GPU memories. You might remember this slide where we show what are the different memory spaces that threads running on the same block and in different blocks can access. A thread has access to its own registers where typically we are going to allocate automatic variables. All different threads inside the same thread block can share data through this shared memory or a scratchpad memory that is an on-chip memory. It's a small memory inside each of the GPU cores, and threads in different blocks can access data in the global memory, and part of it is, for example, devoted to the constant memory, a part of the device memory that is specifically for constants. We saw some examples in the previous lecture, and we talk about about tiling as an optimization technique, and we applied it to matrix multiplication. Remember that the key idea is to declare arrays in shared memory where we are going to store the tiles that we read from the global memory, and we put them in the shared memory, and then we are going to perform the multiplication of these submatrices residing in the shared memory. And that's basically what we do in this part of the code. We go to the global memory to read a tile of A and a tile of matrix B, and we place them in the previously declared arrays in the shared memory. We need to synchronize in order to make sure that all threads, all warps of the thread block are done with this operation, with loading the tile into the shared memory, and then we compute with the tile. As you can see here, multiply and accumulate operations. Before we go to the next iteration, before we go to the next pair of tiles, we have to synchronize again to make sure that all threads in the thread block and all warps in the thread block are done with the computation using the tile. Okay, let's now start talking about these GPU performance considerations. As I said, we are going to spend our time speaking about the main GPU performance considerations and what are the main bottlenecks in a GPU program that we should try to avoid. I would say that there are two main bottlenecks in GPUs, and these are both related to the movement of data, either from the CPU memory or the main memory of the system to the GPU memory or global memory, or directly inside the GPU accessing data from the global memory. In the first case, for CPU, GPU, and GPU, CPU data transfers, the problem we have, the inherent bottleneck that we have is that we need to move data over some bus that even though their speed, their bandwidth is increasing over generations, but they are still limited as compared to the access to data in memories like the main memory of the CPU or the global memory of the GPU. So because we need to move, especially this happens in the systems with discrete GPUs, because we need to move the data over these bus, regardless of whether it's PCI Express or something faster like NVLink, it's very likely that we will have a bottleneck there that we should avoid by amortizing this data movement with computation on the GPU side. And then the second one is the access to global memory. When we are running threads on the GPU cores, we need to access data from the global memory, and these accesses, as you may remember from the previous lecture, take hundreds of cycles. So let's see what are the considerations related to the memory access first. Remember that GPUs are fine-grained multi-thread architectures, and they have the ability of high long latency operations. And one of them, and the most important of them, and actually the most time-consuming of them, are the accesses to the global memory. The way to hide this latency, or at least partially hiding this latency, is by running threads on the core. in order to do so properly, we have to take into account one metric or one parameter that is called the occupancy, which basically defines what's the number of threads that we have running on a specific GPU core. We are going to define the occupancy properly in a later slide. Another important consideration is how we access data. And in order to be efficient when we access data from the global memory, we should try to have coalesced memory accesses that, as we will see, are basically memory accesses where threads that are neighbors, threads that belong to the same warp, access memory locations that are neighbors as well, that are physically located nearby. And another thing we have to try to take advantage of is data reuse. Whenever we have data reuse in our program, as we have seen in the example of the tile matrix multiplication, we should try to take advantage of this data reuse by using techniques like tiling, typically in shared memory or also in registers. Today, we will briefly recap on what we did tiling in shared memory. In a later lecture, we will also talk about tiling in registers. Another important consideration is SIMD or warp utilization. Remember that the SIMD architectures execute threads, different, operate on different elements of a vector or an array in lockstep. So in a GPU, all threads belonging to the same warp are making progress all together. If we have divergence, what will happen is that some threads will operate first and other threads will operate later. And basically what this happens is that we are duplicating or we are making larger the total number of cycles, right? So that's something that we want to avoid. That is called divergence. And we will see that there are some things that we can do, some ways of optimizing our code whenever there is a risk of having intra-warp divergence. There are other considerations as well. They are very useful and important. Atomic operations, they are useful because they allow us to avoid data races whenever we have, for example, two threads in the same warp that need to update the same values in memory. We can use atomic operations in order to have a code that is functionally correct, but the consequence will be or the undesired consequence will be that the execution will serialize. Over this course, we will also talk about techniques to avoid deserialization, to optimize the use of atomic operations, but it's something that will likely happen in our code whenever we use atomic operations, and we should try to avoid or even avoid the use of atomic operations if that's possible with a different algorithm. And finally, and going back to the beginning as well, data transfers between CPU and GPU. As I said, especially in systems with discrete GPUs, we have to move data through the PCI Express bus or through the NVLink bus, but we should try to amortize the cost of these transfers by computing on the GPU for enough time. There are also ways of overlapping communication and computation, as we will see at the end of this presentation. Whenever we have different chunks of data that are independent of each other, we can partition the computation in a way that first, we move a chunk of data, we start operating on that chunk of data, and at the same time, we start moving the next chunk of data. This way, we manage to overlap computation and communication, and in the end, we will see performance improvement in our program. Okay, let's start with more details about the memory access. Remember, GPUs are fine-grained multi-thread architectures, and this allows us to hide latencies by interleaving the execution of instructions from different warps. For example, if we have warp 0 that needs to go to memory to fetch one cache line that will be needed for later operations, we can issue, or the thread scheduler or the warp scheduler will issue instructions from different warps, and the execution of these instructions will hide this long latency operation. So that's the key, and that's the key idea and advantage of fine-grained multi-thread architectures. But in order to do so, we should have enough threads, enough warps running on the GPU core or the streaming multiprocessor in NVIDIA terminology in order to hide those long latency operations. This number of threads, or the ratio of threads that are active or warps that are active with respect to the maximum one that we can have in a GPU core, is called the occupancy. In order for you to see what's the effect of the occupancy, let me show you a very naive example, a toy example here. Imagine that we have the execution in a mini GPU or in a toy GPU. We have the execution of 4 active warps. The execution of instructions is interleaved on the pipeline. For example, first instruction is for warp 0, instruction 3. Next instruction is for warp 1, instruction 2. And at some point, in some warp, for example, warp 0, needs to execute a long latency operation. For example, a global memory access. If we have enough warps, if we have enough threads running on the GPU core, then we can hide this long latency operation by issuing instructions and executing instructions from different warps. But imagine that the occupancy is not that high. We have half of these active warps, let's say. At some point, while warp 0 is going to the global memory, we will see that there is a gap here. So we are wasting cycles in the pipeline. We are not really using the pipeline properly, and the performance will be definitely affected. Occupancy is something that depends on the usage that we do of the GPU resources, or the resources in the GPU core. So it's related to the maximum number of warps that can run in an SM, the maximum number of blocks that can also run in an SM, because there are specific resources in the GPU core that need to be used to keep track of the execution of warps and blocks, and the total amount of these resources is limited. But there are also limitations related to the register usage. You know that each thread is working on using its own registers. In the end, the total amount of registers is limited. Here you have some reference numbers that might be not the most recent ones, but at least they are in the ballpark of existing GPU architectures. One is the register usage. Typically, the register file is 256 kilobytes, or the shared memory usage as well. In older GPUs, it used to be 64 kilobytes. In more recent GPUs, it's, I believe, up to 192 kilobytes. In order to know what's the occupancy, we should take into account what's the use that we are doing of these resources. What's the number of threads per block? That is something that the programmer defines. Remember, in the execution configuration, when we launch the kernel, the number of registers per thread, that is something that the compiler can tell us, because the compiler allocates the variables that each thread is going to use into registers, and the shared memory per block. That is usually something that is defined by the programmer as well. Remember, in the beginning of this lecture, the example of the tile matrix multiplication, where we declare arrays in shared memory of a certain size. There used to be an Excel sheet, a pretty nice one, to calculate the occupancy, taking into account the previous parameters, like the number of threads per block, the register usage, and the shared memory usage. Now, NVIDIA has replaced this Excel sheet with the occupancy calculator that now Insight includes, and basically provides the same functionality. So now that the occupancy is more or less clear, let's go into the details of how memory is accessed. By the way, I would like to clarify something about the occupancy. It's not so important to have very high occupancy in all kernels. That depends on our program. Typically is, especially when we are starting to learn GPU programming, is a good practice to try to maximize the occupancy, but not necessarily 100% occupancy is going to provide the best performance for all different kernels. And the reason for that is that there might be contention as well when accessing some resources like global memory or shared memory, if we have too many warps, let's say, for a specific program. But in general, it's a good idea to try to maximize the occupancy. With respect to the memory layout of a matrix, as we already know, two-dimensional data structures like matrices are usually stored in C in a row major layout. What that means is if we have a matrix like this one, this matrix is laid out in this way. First, we have all elements of the first row, then we have all elements of the second row, and so on and so forth. So as we are going to see next, for an efficient access to the global memory, we want to access elements that are consecutive. So it will make sense in your program for better access to the global memory to access first elements of row 0, then elements of row 1, and so on and so forth. And the reason for that is how DRAM is internally built and how data is accessed in DRAM memory banks. Let's see a very simple example, a toy representation of a DRAM bank operation. A DRAM is composed by memory arrays with rows and columns of DRAM cells. And the way that we access data in these rows and columns in these cells is by using a so-called row buffer, which basically is an array of sense amplifiers, each of them connected to each bit line or each column of the DRAM memory array. So whenever we want to access data from the DRAM bank, we will have to open rows and then access these rows, which basically, as you will see, means moving the row from its original location, the contents of the row from its original location to the row buffer, and then we will read and write the data in the row buffer. So in the very beginning, the row buffer is empty. At some point, we want to access one element, the element located in row 0 and column 0. So what we do is providing the row address, which are some certain bits of the address, to the row decoder, and this row decoder will activate one specific row, in this case, row 0. So what happens next is that the entire row goes to the row buffer, and then using the column multiplexer and using the corresponding bits of the address, the bits that correspond to the column, we can start reading elements from the row. This would be column 0. And then if the next access goes to column 1, because it's also in row 0, the row is already in the row buffer, we are saving the latency of moving the entire row to the row buffer because we already did that in the previous access. And now we can directly access column 1 from the row buffer, as we can see. And if it's column 85, exactly the same because it's as well in the row buffer already, so we can read it directly from the row buffer. But at some point, we may want to access data in a different row, for example, row 1. What happens is that row 1 is not in the row buffer, so then we have what we call a row buffer conflict. And what this means is that we need to close the row, row 0, and open the next row, row 1. And this takes, again, a longer latency because we have to move the entire row to the row buffer. And then at this point, we can access elements from row 1, this column 0 in row 1. So these rows are also called DRAM bursts. And as you have just seen, if we access data that resides in different bursts, we will have to pay this long latency of opening the row, basically transferring a new row from its original location to the row buffer. So if we have two consecutive accesses to columns or to values, data that resides in different rows, we'll have to pay the long latency of opening row 0, access the data, and then pay the long latency of opening row 1, and then access data. However, if we access data that resides in the same row or in the same burst, we can save the time of opening the row for the second and subsequent accesses, as you can see here in this timeline. So accessing data in the same burst is faster than accessing data in different bursts. At this point, because we still have to pay long latency to open the row, even if we are going to reuse them later, or we are going to hit in the row in later accesses, it's good to try to take advantage of other techniques that on other mechanisms that can improve the access, the performance of the memory accesses, and basically increase the overall bandwidth. And one way to do so is memory banking. That is a technique or is an approach that we already know from a previous lecture. Basically, what we have in memories, in all kinds of systems, and in particular in parallel systems like GPUs, are banked memories or interleaved memories that basically divide the entire memory space into different banks that can be accessed simultaneously. And this way, we can overlap the access latency or the initial latency of opening rows in different banks. We are going to see what are the positive effects in the GPU in this case. We can do this multiple banking, and we can do something similar with multiple memory channels. We are going to talk about both. Multiple banks enable concurrent DRAM accesses, as we are discussing, and we are going to see in the next slide as well. And basically, different values, different data elements reside in a bank depending on some bits in their address. We can do, for example, word interleaving, which means that an entire word of, for example, 32 bits resides in bank 0, the next one in bank 1, the next one in bank 2, and so on and so forth. And something similar we can do with different channels. Different channels means basically that we have more than one memory bus. This has the additional advantage that we increase the bus bandwidth as well, because basically we are giving more resources to our system. We are placing more banks, so we have more, we are placing more channels, so we have more buses for communication between the memory and the host. However, it's important to keep in mind that we may have conflicts both when we use banks and when we use channels. And this happens if we have different threads in the same program that want to access data that resides exactly in the same bank or exactly in the same channel. In that case, the accesses will be serialized. There are techniques of avoiding or alleviating these potential conflicts, for example, randomizing with hash functions, basically applying XOR to different bits of the address, and as well as what we normally do, which is assigning lower order bits to the banks and the channels, because they typically have more entropy. That's why I gave earlier the example of placing consecutive elements in consecutive banks, for example. We are going to talk a little bit more about these techniques to try to avoid the bank conflicts. But let's first see how the latency can be hidden even more if we use multiple banks or multiple channels. In this specific slide, we are going to talk about the multiple banks. If we have one bank, time is still wasted in between bursts, right? Because we can open one row and take some time, then we perform several accesses to that row, and then we have to close the row and open a new row. So still, as you see, we are waiting a long time in this timeline. If we have multiple banks, while we are opening one row in one particular bank, let's say bank 0, we can be accessing values in the next bank, let's say in bank 1. And in the end, we are taking advantage of the bandwidth. We are really maximizing the bandwidth here, because if these banks are in the same memory channel, we can, so these accesses here are making use of the bus while we are opening a row in a different bank, like this bank 0 or in bank 2. So as you see, we are overlapping the long latency as well inside the DRAM memory array, the long latency of opening the row, with accesses to rows that are already open in different banks. And this way we can maximize the bandwidth. And we can do that better if we have high occupancy in GPU cores. Of course, if you have only a single thread running on an entire GPU core, you cannot sustain so many memory accesses. But if you have many warps, many thread blocks running in the same core, it's more likely that we can access multiple banks at the same time, and this way maximize the overall bandwidth. The best way to do so is to try to have coalesced memory accesses, or make sure that our accesses, we are doing memory coalescing. That basically happens, as we have seen, when the threads inside the same warp, when threads that access memory all together are accessing consecutive memory locations, because these consecutive memory locations will likely reside in the same DRAM burst. And if that happens, we can talk about memory coalescing, and our overall bandwidth will be maximized. However, if threads in the same warp, remember that threads execute in lockstep, so they go to memory all together. If they access locations that are not in the same burst, we will end up needing more than one memory transaction for each of them. And we may end up having even band conflicts or channel conflicts if these threads belonging to the same warp try to access data from the same bank, or try to access data from the same channel. So in the end, multiple memory transactions, and this will definitely provide or cause reduction in the sustained memory bandwidth. This is sometimes called uncoalesced memory accesses, or sometimes called memory divergence, and it's something that we should try to avoid. So in summary, the access to global memory is going to be more efficient when the memory accesses are coalesced, and this happens when concurrent threads access nearby memory locations. That's the way of achieving peak bandwidth, maximizing the sustained bandwidth. And as an example, think about all threads in the warp accessing one cache line, or accessing several consecutive cache lines. In this specific situation, we don't have coalesced memory accesses. Why is that? Because thread 1 and thread 2 belong to the same warp, and the way that they are accessing data from this matrix is this way. So in their first access, thread 1 wants to access here, thread 2 here. The second access, thread 1 wants to access here, thread 2 here. And as you can see, these two elements here, or these two elements here, do not belong to the same cache line. There is a strike between these two elements, right? However, if we access the memory in this way, we access the matrix in this way, with thread 1 accessing here and thread 2 accessing here, the elements that each of the two threads needs to access in each iteration these are nearby memory locations. These are neighboring elements. So we will likely have coalesced memory accesses, because these elements will likely belong to the same cache line. In order to give you more details, or a more clear example, uncoalesced memory accesses, when the direction, the way that the threads access values in different rows is horizontally. So for example, thread 1 or thread 0 accesses here, thread 2 accesses here, thread 3 accesses here. Observe that there is a distance between these accesses. So problem here is that we are going to have multiple memory transactions, and it's something that will be repeated in later iterations as well. However, if we access in this direction, then threads in the same warp are going to access nearby consecutive memory locations, and this will be in the first iteration, in the second iteration, etc. And for each of these accesses, we will have just a single memory transaction. There are still ways of improving coalescing by using shared memory. Remember that when we operate with matrices, we typically use tile access patterns. We are going to use tiles in the scratchpad memory or in the shared memory. So the first thing that the threads do is go into the global memory, reading one tile and placing it into shared memory, and then we can perform the accesses in the shared memory directly. So even here, where we have the threads accessing horizontally, now that the tiles are in the shared memory, we are avoiding the uncoalesced memory accesses, because the tile itself can be loaded in a coalesced manner, right? We can have different consecutive threads accessing consecutive elements of the tile and placing them in the shared memory altogether. So shared memory can be used to improve coalescing. This is a technique that sometimes is called corner turning in some sense, because we first access this way, and then we access this way from global memory to move the data to the shared memory, and then threads access this way in shared memory. Shared memory, as you know as well, is going to be very useful when there is data reuse. Remember the example of this Gaussian filtering. Here we assign consecutive pixels of the image to consecutive threads, and there is a lot of data reuse. For example, these pixels here, all these 6 pixels here are going to be used by the threads assigned to these elements here. So there is where we can use shared memory tiling. We load an entire tile of the image into the shared memory, and then we operate directly on this tile in shared memory. But shared memory is an interleaved or banked memory. You know, good thing of this type of memories is that each bank can be accessed in parallel, and each bank will be servicing different addresses per cycle. There are typically 32 banks in the shared memory of NVIDIA GPUs, and the way that we place consecutive elements based on their address is by interleaving them, right? Address 0 goes to bank 0, address 1 goes to bank 1, and so on. But there might be bank conflicts, and this will happen especially when we have S-threaded memory accesses. These bank conflicts happen inside the same warp. Why is that? Because threads of the same warp execute together. Remember that the instructions in the pipeline are issued for each of the warps individually, and the execution of instructions from different warps is interleaved. So this avoids bank conflicts between different warps. Still, inside the same warp, this is really risky and can really affect our performance. Let me give you very briefly some easy examples of what are bank conflict-free accesses and accesses with bank conflicts. For example, if we have consecutive threads accessing elements in consecutive banks, what happens when we have an stride 1 in our accesses, then there is no bank conflict. Or for example, if we have randomized accesses and different threads access different elements in different banks, in this case, there is no bank conflict. We will talk about n-way bank conflicts depending on what's the stride when we have different threads in the same warp accessing data in the same bank. For example, if our stride is 2, what will end up happening is that, for example, thread 0 and thread 8 will access values in bank 0. Basically, what this means is that we will need twice the latency to access the data from the shared memory. And this can be even worse. Imagine that the stride is 8, and in this case, we are going to have an 8-way bank conflict. There are ways of reducing in software the shared memory bank conflicts. One potential way is using a technique that is called padding. Let me give you the very simple example. Imagine that the stride is 32, the number of banks is 32. That means that the 32 threads of the warp all want to access data in bank 0. For example, thread 0 accesses element 0, thread 1 accesses element 32. What we can do is just padding with one empty memory position such that the 32th element, or the 32th memory location occupied by a specific array is completely empty. And the element, the value that was originally in address 32, now is in address 33. And address 33 is in bank 1. So what that means is that thread 0 accessing element 0 accesses element 0 in bank 0, and thread 1, which needs to access element 32, is no longer accessing bank 0, but bank 1, because this element 32 is in address 33. That's padding. It's pretty simple, as you see, and very useful in many different workloads. There are more sophisticated approaches like randomized mapping or like hash functions. If you want to, I mean, there are many classic papers like this one from ISCA 1991 by Bob Rao that you can check. But if you want to check a more recent one where we propose the use of XOR-based hash functions, both in software and in hardware, I can recommend you this more recent paper. I mentioned as well, another important performance consideration is SIMD utilization. Remember, we execute warps, the threads in these warps run in lockstep, so they are all together. If we have divergence, then the performance will be dramatically affected. In a code like this, where odd number threads go in one direction and even number threads go in another direction. Like, for example, even threads do this and odd threads do that, as you see here. What will happen is that our warp is going to diverge, and half of the threads go through the if, half of the threads go through the else, and this means that we are basically requiring, let's say, twice the number of cycles to execute the warp. But now imagine that we have two entire warps here, 64 threads, and we assign elements to the threads in a different way, in a way that all threads with thread ID less than 32 do this, and threads with thread ID greater than 32, 33, etc., they do that. This case, we are assigning the computation in this way. So all threads of warp 0, threads from 0 to 32 do if, so there is no divergence, and the threads in the other warp do else, so there is no divergence. This is or a very good example of this intra-warp divergence happens in a naive implementation of vector reduction. If we have threads, if we assign threads like these, such that thread 0 adds element 1, 0 and 1, thread 2 adds element 2 and 3, and so on and so forth, we see that half of the threads are already not working from the very beginning, and they keep retiring over iterations. This is a vector reduction as a tree-based approach that we are going to cover in a lot of detail in a later lecture for the corresponding parallel pattern. But as you see in this implementation, there is a lot of warp divergence because many of the threads are not doing anything. There are ways of optimizing this, assigning basically the computation to threads in a different way, because a parallel reduction in the end will end up having one value, and because reduction, if it's based on addition, has the commutative and associative properties, the way that we add the elements doesn't make any difference in the final result, especially if we are operating on integers. So what we could do is assigning consecutive threads to consecutive elements, and then have these threads performing the reduction with elements that are far away from them. Whenever threads start retiring, all the threads that continue working will be consecutively numbered. And this means that we are reducing the probability of intra-warp divergence. But anyway, we will see this example with much more detail in our later lecture about parallel reduction. Next consideration, atomic operations. They are very useful because we can use them to avoid data races whenever we need to have threads accessing the same data structure to perform read, modify, write operations. Atomic operations started at some point in the initial times of CUDA, and they were first enabled to the global memory, then to the shared memory, and now they have improved a lot. Even their performance have improved a lot with the specific hardware, as we can cover in a later lecture, that optimizes its performance, but still there is a performance bottleneck if we have serialization, as we are going to see. This is the typical definition of an atomic operation. An atomic add is one of the atomic functions or arithmetic functions that can be performed in an atomic way. And as we see in this atomic add, there is a pointer to the shared memory or the global memory, the element in shared memory or global memory that we are going to update. There is a value to add in this case, or to subtract, or to calculate maximum, etc. And then there is a value that is returned, that is the old value, the value that was contained in the shared or global memory before we perform the update. There are also atomic operations for bitwise functions and for different data types. Atomic operations are very useful whenever we need to have concurrent accesses from different threads running at the same time to data structures, but they have the problem that this serialized execution. If two threads, thread 0 and 1, need to access two elements that are in shared memory but are in different memory locations, the two values that are in different memory locations, then they will take some time, but in the end, things will work well. There is no conflict here. However, if these two need to update data that resides exactly in the same memory address, then we will have an extra latency due to the atomic conflict. Atomic operations, as I said, they are useful to prevent data races. We can consider that there are two different uses of atomic operations. One is for computation, when we are really using them to calculate the output of a kernel. For example, in later lectures, we are going to see the example of the use of atomic operations with the parallel reduction or with the histogram calculation. And atomic operations are very useful as well whenever we need to synchronize different threads running together, for example, to implement logs or counters or flags to signal another thread that some certain computation has been done, etc. We will see different examples of over this course. Okay, we are approaching to the end. Asynchronous data transfers between CPU and GPU. Remember that I talked in the beginning about overlapping computation and communication as a way to alleviate the cost of moving data from the main memory to the global memory of the GPU. And the way to do so is by taking advantage of the asynchronous data transfers that exist in CUDA and in OpenCL that are enabled by GPUs. In CUDA, this is done by using a feature that are called the CUDA streams. A CUDA stream is basically a sequence of operations that are performed in order. We basically tell the driver that something is going to happen in order and we need to respect this order. For example, a data transfer, kernel execution, or a data transfer in the opposite direction from the GPU to the CPU. These are very useful whenever we can divide the computation into different chunks that are independent of each other. Imagine that you want to do a vector addition. And in vector addition, we perform the element-wise addition. So whatever computation we do on element 0 has nothing to do with the computation that we do on element 128. So we can partition our arrays and we can start transferring chunks of the input arrays and start computing on those chunks while other chunks are being transferred. That's the basic idea. For example, we can divide our D input data instances and our V blocks into different chunks, the number of streams that we are going to use in our code. And this way, we can transfer one chunk, start operating on that chunk of data or those chunks of data, and at the same time, we continue transferring data in different chunks from the CPU to the GPU and vice versa. We can estimate the performance improvement provided by the CUDA streams and the asynchronous transfers by using these simple estimates. One for the case where the kernel is dominant, it takes longer than the transfers, and the other one when the transfers are the dominant part of the execution. And this is pretty useful in many different applications. In this paper here, you can see several examples. Here you have a toy representation of how to take advantage of CUDA streams and the asynchronous transfers when doing video processing. Instead of transferring all frames to the device and then computing on all those frames as we are doing at the top of this figure, we can partition the operations because we typically operate on different frames independently. So we send consecutive chunks of frames to the GPU. We start operating on those chunks of frames while we are performing the data transfer when we are moving data later frames to the GPU memory. And in the end, we can save significant amount of execution time. You can see more details about this example in the longer version of this lecture. So in summary, performance considerations, data movement is always key bottleneck. CPU, GPU, and GPU, CPU data transfers and global memory accesses. There are ways of optimizing the memory accesses. First of all, try to take advantage of the latency hiding mechanisms of the fine-grained multi-thread architectures, in particular GPUs, by having enough occupancy, enough threads running to perform this latency hiding mechanism or take advantage of this latency hiding mechanism. We should try to have coalesced memory accesses, basically consecutive threads access nearby memory locations. We should take advantage of data reuse. For example, in shared memory, in later lectures, we will talk about data reuse in registers as well. And we should avoid warp divergence, basically maximize the utilization of the SIMD units or the warps. There are other considerations, such as the use of atomic operations that can cause serialization, and related regarding the CPU to GPU transfers. One way of optimizing them, if it's possible, is to partition the data into multiple chunks that are transferred and operated on independently, and this way we can overlap communication and computation. Recommended readings for these lectures, Chapter 6 and Section 20.5 in Chapter 20 of the book Programming Massively Parallel Processors. And for sure recommended the longer version of this lecture, where we provide a few more details about all these different GPU performance considerations. This is all for today. I really appreciate your attention, and I hope to see you in the next lecture.